All right, let's have a look at this Markov chain example. It says that commuters traveling to the city can travel by car, bus, or train, and each month the preferences of commuters change in the following way. So, of the car drivers, 80% stay with cars, 10% go to bus, and 10% change to train. Of the bus travelers, 65% stay with bus, 25% change to train, and 10% change to car. And of the train travelers, 90% of them stay with the train and 10% change to the car. At the beginning of January, now we need to think about our timing with these as well. So the beginning of January 2021, 1,800 people were using cars, 2,200 were using a bus, and 3,000 were using the train. And they want us to draw a diagram to represent the transitions. Now, before we even start, let's start with defining our variables. Okay, so let's let CN, so car, bus, and I'm not going to call train T, just because with Markov chains we've got a transition matrix and that's a T, so I'm going to say rail, okay? And I'm going to say that's the, and this is important, the proportion, okay, of people who use cars, buses, and trains at the, and here we have the start of the nth month since January 2021. Okay, so I've defined my variables quite nicely there. Let's have a look at what my diagram can look like. So we have our cars, we have our buses, and we have our trains. Put my buses down here and our trains over here. And we can say that of our car drivers, 80% are going to stay with cars and 10 and 10. So 80% are going to stay with cars, 10% are going to trains, and 10% are going to buses. Then I look at my bus people, 65 stay with the bus, 25 change to train, and 10% to car. So I have a 0.65 staying with the bus. I have 10% going to car and 25% going to train. And then of our train people, 90% stay with the train and 10% go to car. So I have 90% there and 10% going back to cars. So that's our diagram that's going to represent what is happening every month with my commuters. Now, they're asking us to calculate the number of people, so the number of people using car travel at the beginning, so we're talking beginning of June 2021. So if the beginning of January is our initial date, we have beginning of February, beginning of March, beginning of April, beginning of May, beginning of June, we're actually looking there at S5, okay? So we might just want to make a little note there. S5 will be my beginning of June. Okay, so where do we need to begin? Okay, so here's B. We're going to say beginning of June 2021 is going to be equivalent to S5, and I need to set up my transition matrix. So from my diagram, and this is about being consistent, okay, so T, and we're going to write in our from and our to make sure that we're being consistent here. We've got C, B, R, and C, B, R. And we're talking proportions here. There's my matrix. So car to car, 80% stay with car, 0.8. From car to bus, 0.1. From car to rail, 0.1. From bus to car is 0.1. Bus to bus, 0.65. And bus to rail is 0.25. And then rail to car is 0.1. Rail to bus is 0. And rail to rail is 0.9. All right, now we've got our transition matrix, but we first need to figure out what our initial proportions, so our S0, our initial matrix is, okay? And in order to do that, we need to figure out what our proportions were initially, okay? So our proportions of car travelers, well, it said to me that 1,800 out of a total of 7,000 people traveled by car. So that's 0.2571. My bus travelers, I had 2,200 out of my 7,000 people. And that's 0.3143. And my train travelers were going to be 3,000 out of my 7,000, and that's 0.4257. I'm going to represent these in a matrix in fraction form, just so that if there were ever any rounding errors or problems, I wouldn't have to deal with them. So therefore, my initial matrix is going to be 1,800 over 7,000 and 2,200, 7,000 and 3,000 over 7,000. Good. Okay. Now, in order to find my proportions at the beginning of June 2021, my Markov chain formula says that I have to say it's S5 is equal to S0 multiplied by my transition matrix to the power of 5. And that's going to be 1,800 over 7,000, 2,200 over 7,000, and 3,000 over 7,000 multiplied by 0.8, 0.1, 0.1, 0.1, 0.65, 0.25, 0.10, and 0.9 to the power of 5. And using your graphics calculator, we have that S5 looks like this: 0.320528, 0.112724, and 0.566748. And those correspond to cars, buses, and trains. Okay, so therefore I can say, therefore, 32%, approximately, let's make it approximately 32% use cars, 11, were they only asking for how many people used a car? Oh, it was only for cars. Okay, so we don't need to go. So 32% use cars at the beginning of June 2021. Now, in order to work out the number, we need to make an assumption that we've got a closed system, okay? Because if we've got more people coming into the city, then it's affecting our percentages. So we have to assume that there'll always only be 7,000 people in the city. So assuming a closed system, number of people using cars will be 0.3205 times by my 7,000 people, and that's 2243.696. Now, obviously, we can't Frankenstein people, so therefore, approximately 2243 people are using cars at the beginning of June 2021. Awesome. Okay, next part of it is use matrix methods to calculate the long-term distribution of commuter travel. Okay, we have to show our working using the matrix methods, and this long-term distribution tells us we're looking for the steady state, okay? And you will not get full marks if you just put it to a large power, okay? You have to show the working for the steady state. Okay, so assuming a steady state exists, okay, if we have a steady state, that means that our proportions that we want to get will be our initial proportions multiplied by our transition matrix. Okay, so what it looks like is going to be CBR is CBR multiplied by my transition matrix here. Maybe I should have written the formula down for the steady state. So our S steady state is going to be our S steady state times our transition matrix. Okay. And from that, if I multiply the CBR, so we're looking on the right-hand side now, and we're going to create some simultaneous equations. Okay, so if I multiplied these out, I would actually get that C is equal to 0.8C plus 0.1B plus 0.1R, and that's equation 1. I'm going to get that B is going to be 0.1C plus 0.65B plus 0R, and R is going to be 0.1C plus 0.25B plus 0.9R. And the way I'm getting these equations is I am performing matrix multiplication. So I'm saying CBR multiplied, so row multiplied by column, and that will give me my first entry for C, and then row multiplied by column 2 will give me my B, and my row multiplied by column 3 will give me my last entry for R. Okay, and I need to just rearrange these so that I can get all my variables in the same order, because if I'm going to use simultaneous equations with my calculator, I need to have all my variables in the same order. So from equation 1, I'm going to just rewrite this so that I can take the C over here, I'm going to take to the other side, so that I have negative 0.2C plus 0.1B plus 0.1R is equal to 0, and I'm going to make that equation 4. And then from equation 2, now I need to take this B across, so I'm going to have 0.1C, notice I'm lining them up, minus 0.35B is equal to 0. And then from 3, I'm going to have 0.1C plus 0.25B minus 0.1R is equal to 0. Now, we can put plus 0R there just so that we make sure we line things up when we are using our graphics calculator. The final thing we need to do, because we're dealing with probability and proportion, we have got another equation that says C plus B plus R. So our proportions of people using those transport is equal to 1. And that's pretty much the key to all of our calculations. So what we're going to do now is only use 3 of the 4 equations, but we definitely have to use this final one, okay? So we're going to say using 4, 5, and 7, okay? And I'm going to put them into a matrix now, okay? So let A be, so I've got negative 0.2, 0.1, 0.1, 0.1, negative 0.35, 0, and 1, 1, 1. Okay, and let X, my variables are going to be C, B, R, and I've kept everything in that order so that I'm making sure I'm okay. And B is going to be my answers, so 0, 0, and 1. Because what we have then is we have AX equals B, and I can use inverses to help me to find them. So inverse AX is inverse AB, IX, and remember we always show all this working, X is inverse AB, and I'm going to put it into my calculator. So using my GDC, X is going to be the inverse of A, so negative 0.2, 0.1, 1, 0.1, 0.35, 1, 0.1, 0, 1, to the negative 1, and 0, 0, 1. And I can then say that CBR is equal to 1/3, 2/21, and 4/7. And we can interpret that. So we could say that C is approximately 0.33, B is approximately 0.095, and C is about 0.571. And so we can say, therefore, in the long term, approximately 33.3% use cars, 9.5% use buses, and 57.1% use trains.